Great. Thanks so much for the intro, Jim. We were going to do our intro, but we can go ahead and get started. So yeah, I'm Chris. We have Kaavya and Jean here, and we'll pass it off to Jean to take us on the start of our talk.
Yeah, hi everyone. Today I'm going to present Risk Knowledge Platform together with Kaavya and Chris, and here's today's agenda. First, we'll start with platform overview, then deep dive into UFlow and uGraph feature store, then later the use case for machine learning of risk assessment. Next. So why Risk build this feature store? The motivation is Risk needs a scalable self-service feature engineering platform for computing features for predictive decisioning and machine learning purpose. The use case includes payment fraud, promotion abuse, GPS spoofing, account takeover, and so on. Next. Here's the architecture of the Risk feature store. So when an event happens, for example, when user take a trip or user signs up, this kind of events will hit the risk decisioning service, and then the risk decisioning service will fetch the features from knowledge platform, includes uGraph and UFlow. So all the features are managed by a feature spec, and then both uGraph and UFlow have DB write log. And together with the event log of the decisioning service, both will contribute to the feature time travel tool that Chris is going to present later. Next. So here's the end-to-end feature engineering flow. The data analysts and data scientists will try to explore and analyze what data is useful for building into a feature. Then they will go through the feature engineering process and then feed these features into machine learning models and rules, and result in potential actioning like ban, warn, or error. The latter two steps are called decisioning, and then the decisioning result will contribute back to the feature iteration. Next. Yeah, so let's deep dive into the UFlow feature store. The UFlow computes three types of features: batch, near real-time, and real-time. All the features are managed in the following four aspects. First is the feature catalog. It has all the definitions of the features. And then we have, next is the feature quality. The users are able to access the metrics of feature correctness, distribution, completeness, freshness, and anomaly detection when they want to explore. And when the users want to debug, they can trace up and downstream of the feature by the feature lineage, and then try to find the feature correlation between each other. And when people create, evaluate, or deprecate a feature, then that's the when the feature lifecycle comes into the picture. Next. So here is how our batch feature computation work. The data source is from Hive. It can be self-computed or externally pre-computed. And then the Hive data is dispersed into Cassandra with the support of auto bootstrap, auto backfill, and CI/CD. And during the dispersal, there will be feature level optimization. Like, for example, we only disperse incremental changes to save the computation resource. And we disperse the data with TTL, so it can save some storage costs as well. The end-to-end development is all spec-driven, so it's non-engineering friendly. Next. So next is a near real-time computation. The data flows from Kafka to various kinds of things. And then all the pipelines enables feature write log and the DLQ support. And all the data quality metrics are handy for people to explore. So for some compliance use cases, we also enables the end-to-end exactly once processing for them. So the backfill from Hive is also supported for this computation. And for the complex use cases, we have RPC fanout. Early termination is supported for optimization of performance. So for different use cases, all of them are decoupled for the resource and computation, and multi-tenancy is supported. Next. Yeah, so both the mentioned batch feature and near real-time features support aggregation. So our aggregator has aggregation function like sum, count, and so on. And the window can start from minutes to hour to day or year or lifetime to date. Yeah, and then all the computed features will go to Cassandra and then will be fetched in our real-time service, which comes in the next slide. Yeah, so here is our real-time service architecture. It has two parts. One is the feature access and one is the feature update. So for feature access, we enable cache for it, and hierarchical feature fetching are supported. So people can mix and match different gateways, different DBs, different orders, and then to achieve the comprehensive fetching. And then for some use cases that after the feature fetching, we also update back the feature. Yeah, and similarly, the write log is also enabled for the feature update in this real-time service. And for the real-time service, we'll achieve 4 nines availability. And this is all for the UFlow deep dive. And I'm going to hand over to Kaavya.
Thank you, Jean, for that high-level overview of UFlow. Hey, everyone, I'm Kaavya, and I work in the uGraph platform of the knowledge platform team. Next slide, please. So a little bit context about knowledge graphs. So we at Uber have a lot of data about a lot of different entities. To make sense of these entities, a graphical representation is very powerful because it helps us understand unstructured data and convert it into a structural form by representing it through vertices and edges. So the relationship between the vertices help us understand direct and indirect relationship, which are not clearly visible from the unstructured data. And it's also easier to visualize the data and also query it using some of the open source languages that are available. In particular, this is useful in risk context where you want to be able to understand the fraudulent activities that are happening, which are also not easily visible through the data that is as is available. Next slide, please. What is uGraph? uGraph is actually an internal term, and it's an umbrella term that we use for providing both real-time and batch solutions to do feature computation and querying. It supports real-time for point-to-point queries and also batch for ML-based feature computation and also bulk queries, mostly used for deriving insights and also facts. Next slide, please. So the real-time and the batch is what we refer to as OLTP and OLAP. So I'll be talking about the ingestion framework of how data gets inside. So like how Jean mentioned, we also have a spec-driven framework for OLTP and OLAP, where you can specify whether the data is ingested through a Kafka topic or through Hive. And you can specify what vertices and edges needs to be ingested, along with the different properties for the vertices and edges. And the Hive table ingestion, which we often refer to as the bulk ingestion, happens through Spark jobs, which is either once a day or at different intervals in time. Kafka topics are used most for streaming ingestion, which is happening through our Flink-based streaming ingestion platform. And we use Cassandra as our primary database for OLTP. And on top of it, we also have a querying layer that almost always gives you a real-time snapshot of what is there in the current time. Next slide, please. OLAP ingestion framework, similar to OLTP, is also a spec-driven ingestion framework, but we only operate from the Hive tables because it's a batch processing system. But here, the kind of output that we store is in 3 parts. So one is reconciled graph, another one is feature graph, and the other one is intermediate graph. So reconciled graph is similar to the OLTP data, where at any point in time, it gives you a holistic view of the entities in current time. Feature graph is more of an ML-driven use case, which is also a subset of reconciled graph, where you don't have all the entities in the graphical data, but only select entities based on different ML use cases that we need. And it's usually run for a historical point in time. So usually ML engineers come up with a specific use case that want to run for a historical time data. The third one is the intermediate graph, which is used for regenerating reconciled graph in case we miss any data, and also to generate the feature graph for historical time. And it's a date partitioned table, so we can go back for however long we want and then regenerate the data. As similar to OLTP data, we also have a querying layer, and the querying layer, I'll talk about it in later slides, which is a common querying layer used between the OLTP and OLAP. Next slide, please. So to more explain about the feature graph and how it is built. So ML engineers usually want point-in-time historical data. So they come up with a use case, and they also specify what start dates and end dates that they want to run this feature graph for to generate the historical data. So we go back in time, use the data from the intermediate graphs to generate the feature graph, And this is an accumulated data, right? So we do this for successive dates between the date ranges. And then at the end of it, we have one final feature graph, which can be used for querying by the ML engineers. Or you also have the ability to look at the partition data and see how features are changing in between. So this is again a spec-driven framework where you don't have to worry about writing a code. You just have to give us a spec and the system will take care of generating the feature graph for you. Next slide, please. So now that the ingestion and the ML feature generation is done, I want to spend some time about Cypher. So Cypher is the open source query language that's available for querying graph databases. So it was generated or discovered by SQL, based out of SQL. So the syntax is very similar between SQL and Cypher in how you write the query. So here I have a very simple use case where it tries to represent user-to-user relationship that is connected through a phone number. So you have a user vertex and you have a has phone number edge followed by another vertex, which is a phone number vertex. And from the right side, if you see, you have a U2 user that's connected also to the same phone number. So this is a very simple query to connect users between two users who share the same phone number. Next slide, please. So if you want to use this query to generate features, then I've extended the same case to generate unique UUIDs who are connected through the same phone number. So the same query is extended. And in addition to returning the user UUID, you also return the distinct UUID. So you can similarly add relational classes in this. You can also extend it to apply filters like how you would do in SQL. So it's just about how you write the query to extend it for different feature generation use cases you would need. Next slide, please. So how does it all come together? So once you have the Cypher query, you give it to our service, and the service will take care of generating a query plan that is as optimized you would want in the query execution. And then it gives it to a computational layer, where instead of running the query against the whole database, we fetch a smaller portion of the graph database based on the query that you've given us. And then from the returned subgraph, you will compute the query or do the feature computation on top of it and return the response back to the service. So this is at a high level covers what we do with ugraph in risk context. And now I'll hand it over to Chris.
Thanks, Kaavya. That was an amazing overview of ugraph. Yeah, so my name is Chris. I'm a machine learning engineer here on the risk team. I'll talk about machine learning for risk and how we can provide real-time predictions is what I'll start with. Sort of going back to the architecture Jean mentioned earlier, we have sort of user starting off with requesting a trip, and this first flows into our decisioning service. This decisioning service is ultimately where we can provide our predictions and make a decision on certain kinds of requests. For machine learning engineers, this means making calls to Michelangelo, which will serve our machine learning models that can help us evaluate risk across a number of domains. We may have many different models, such as payment fraud models or account takeover models. And let's go about thinking about how we might build one of these models. And maybe we can start with how might we build a payment fraud model? Maybe the goal here is we want to calculate the probability of some kind of payment resulting in fraud loss when, for example, user requests a trip. Of course, whenever we train a machine learning model, we need data. And so the first thing we can start with is in this decisioning service, we have some log of events for every event that we've provided a decision for in the past. And this log may contain many entity values, such as the user that's acting, the payment that they used, the email domain of the user, maybe the fare that the ride costed the user, and maybe the timestamp that the trip happened at. This data is called our basis data. And we can see that if we combine this data with some kind of label that we determine in some fashion, we can train some kind of maybe naive model classifier that can feed in this data and maybe give us a not so good model. And let's think about why, right? The type of data that we have here in our basis data might not be very powerful for machine learning. For example, just using the email domain alone or the ride fare alone, this data may cause the model to overfit on, for example, the ride being very expensive and or certain email domains being very fraudulent, at least when the model is trained. And so what can we do to make it better? Of course, we would like more data, maybe enrich the model with more features. And let's start with how we can do that with batch, right? So I want to dive into how we do batch feature backfill. So the first observation here is that in our basis data tables, we have a few different kinds of entities. We have primary entities. These entities sort of like define the primary actors that are involved in a request. Here we have the user, they're the ones making a trip. And then we also have secondary entities. And these entities are sort of like the entities that are shared among multiple primary actors. For example, the same user may share the same payment, or maybe even share the same email domain. And the observation there is that when we do batch feature backfilling, we can take those secondary entities and pre-compute some kind of entity feature tables across many different metrics to provide feature values for every entity value. In this case, we sort of see that across many entities, such as like maybe an email domain or destination geohash, we can compute features such as like the email domain chargeback over a 7-day window, given that we also are computing for like metric of chargeback in a time window of 7 days. And we can do this for many time windows, many metrics, and many entities, and all the entities that are in our basis table to compute sort of like a product of the number of entities times the number of metrics times the number of windows. And this allows us to extend our training set to at least cover all of these entity feature table features, which gives us a lot of additional predictive power in our machine learning. And you see now we have a high performing model. But of course, like, what are the gaps? Like, when do we need real-time feature engineering or near real-time feature engineering? Well, the answer is like when we want to ask questions like this. How many trips has the user taken in the last 24 hours? If we just do this in a batch fashion, this might not give us an appropriate level or appropriate granularity of accuracy. Or we want to get like some kind of attribute feature like the user's last known phone number, or if there's some new entity value observed for the first time and we're sort of observing the cold start problem, we may see that it doesn't have values populating very well yet, or anything related to graph where we want to count number of like users linked by the phone number to the current user, or even like for the fraud domain, number of banned users linked by the phone number. Any kind of feature engineering on primary entities benefits substantially from real-time feature engineering, which is really relevant for the types of problems that we see in the risk domain, such as account takeover, new user fraud, and marketplace abuse, and even safety. And so let's kind of dive into how do we do near real-time feature backfill and what are the benefits? So the first observation is that for these sort of attribute features that we have, we can use temporal join to stitch their values to our training data set. So temporal join has just been a tool, kind of a term that's like known about for a while, where for every event in your basis data, you get the value of the feature that happened right before. And so this is how we can stitch sort of attribute features to our training data set. And then we can see like the benefit of having near real-time aggregation features for this new.com domain that we saw on the last slide. Near real-time feature aggregation here can sort of help us fill in the gaps that batch feature backfill would have. And the caveat here to all of these like solutions for creating features is that the data must exist in some kind of offline storage. And so the solution that we built for this is we started persisting changes into a write log. And so remember from earlier, we have this sort of solution architecture for near real-time feature computation where data is read from Kafka. And then in our ETL, we may do some kind of RPC to an external data source before we load into Cassandra. This value of this RPC may not exist in historical data, so we also write it to our write log. And this write log is the same write log that lives below ugraph and uflow. And this sort of allows us to persist all the changes to Cassandra features and can later be transformed into a change log. What can be transformed into a change log, you say? Well, one observation we can have is that we can drop redundant writes for attribute feature types. This sort of like gives us a way to implement an optimized change data capture solution. And for streaming aggregation features, like we can maybe relax some of the latency requirements and say that we can do some kind of pre-aggregation to reduce QPS to Cassandra and reduce changelog storage, as long as we say we can aggregate on like a minute level basis. So this is the last slide, but kind of like summing it all up together, one of the main challenges we see is that we want to provide machine learning engineers access to a tool that can construct training data for them. So this is what we have with this time travel tool. Users can specify sort of like their basis table, join keys, and feature groups. And for both batch and near real time, as long as that we have data in DB changelog or in some kind of Hive ingested Kafka, users can specify basis data, use our time travel tool, and ultimately output a new table with a bunch of extended batch and streaming features. And this allows us to transfer from ML with basis and batch feature backfills to ML with near real time feature backfills. Yeah, so that's our slides.
Brilliant. That was a great tour de force of many different contributions you've made to building this system.